Welcome to week 6 Introduction to Machine Learning. My name is Rohan and I'm a TA for this course. So, do you have any questions from previous weeks or any particular questions before we start? Okay. Let me know in between if you have any questions. So week 6, in week 6, we have mainly covered neural networks. So, neural networks are actually very powerful tools, and they have very huge applications, starting from image identification to maybe Chat GPT. So Chat GPT and all these large language models that you see nowadays have their basics in neural network only. Right. So in order to understand the current trend as well as the future trend of uh, AI, you have to understand neural networks. Right. So neural networks are a vast topic, and they, I mean, there are researches going on still in this field. Uh, so we will not cover the entire thing. It's not possible to cover the entire thing, but we'll cover the basics, and at the end, uh, like I will give you some hints on I'll prompt you some models which are in the current trend, and you know for example, what are the models that could be used to build a platform like ChatGPT, right? And I'll guide you in that direction, and I'll tell you which models to look for, and you can like do research on your own and learn more about them. So yeah, that's going to be the agenda for today's session. And I'm planning to take another extra session on 14th of September. You'll be notified by NPTEL as well. It's a Saturday, same time, 7 to 9 p.m. on 14th of September. So let me know if you want me to cover any special topics on that session. So all the weekly sessions will go on as they are going on now. That will be just be an extra session to address any doubts that you have and that has not been answered. That could be from any week, or you know. So if you have any special topics in mind which you want to discuss, which you want me to discuss in more detail, you can let me know. I'll focus on those topics, or we could do some hands-on as well, right? Uh, That also we could do. And basically that it will be mostly a doubt clearing session, and it will be mostly Q&A, basically questions and answers. Yeah, such. Yeah, yeah, you're audible. Mhm. Okay. Okay. Right. Mhm. Yeah. So your question is you are training model to find whether the number is prime or not. Let's say neural network. Yeah. So sorry. Yeah. So what is your question? So yeah, I get the problem statement, but what is your exact question? Mhm. Mhm. Right. Right. So you mean the weights and the overall architecture of the neural network, right? Okay. So I think we'll get into that. We'll do some hands-on on neural networks you know, and we'll get into details of those. And we'll also see how by, manual calculation, how we can get the weights, how the weights are actually being obtained by back propagation algorithm. Okay? We'll see how we calculate the weights and how we define them via gradient descent and what should be the final weights of the neural network. So today's lecture is basically totally on that, totally on your question. So we'll see, and you can ask questions when we go into that part. Okay. Okay. Is there any other question? Okay. Mhm. So yeah. Mhm. Mhm. Sorry. Can you ask your question again? Mhm. Mhm. So your question is about theorems on partial derivatives. Are you hmm. Are you talking about chain rule? Chain rule? Are you talking about chain rule? Mhm. You mean stochastic gradient descent? Okay. Yeah, we will cover that also in this lecture. Okay, so let me go ahead with this lecture, and then uh, you know we can have questions. Okay. So yeah. So what are neural networks? We'll start from the very basic, and so neural networks have their origin in neurons of our brains, right? So this is the on the left is an image of a neuron. So, for example, this is the detailed structure of a neuron. Maybe biologists can explain better, but the main idea is that these are called dendrites. These endings that you see. So, what they do is they receive impulses. The impulses are transmitted in the form of some chemical signals, and these dendrites receive those signals, and then they transport it through the axon. This channel that you can see. And then they end at the axon terminal. And the axon terminal then again releases those impulses to the next neuron, right? And in between, the impulses could be, modified or changed in some way. And after those modifications, they are getting transmitted to the next neuron. And similarly, that is the way that neural networks in machine learning actually works. right? So for example, this is the input. So let's say you have an input response, and your input goes to some hidden layers, and there could be multiple hidden layers as well. Here I have shown only one. So layer after layer, the signal moves, and finally, you see the output, right? For example, let's say you see a cat, right? And you can identify, your brain identifies that, okay, this is a cat, right? So the cat is the input, okay? And it moves through your various neurons, and finally, your output, the response that you say, okay, this is a cat, okay? Or maybe you see a dog, then your input moves in such a way, your output is it is a dog, right? So that's how a classification algorithm also works, right? So for example, one example could be classification of animals, right? So your input could be uh, any animal image that you give, and your output would be like, okay, this is a cat. Cat is the output node corresponding to cat will be one, and the remaining output nodes will be zero. So that is the way you can identify or classify images and so on. We'll see some examples going forward, but that is the basic structure. Okay. So Monica is asking, are derivations important for exam? Yeah. So if if it's a essay type answer, then derivations could be asked for essay type answers. Okay. Right. Okay. So now, what could be the simplest form of a neural network, right? So the simplest form that we can imagine is this perceptron, right? The image on the right. So we'll start from this simple example, and then we'll move forward and try adding more and more layers to it, and try seeing like how the whole network performs. But in this case, you have the simplest model where you have these input nodes, okay, and these input nodes go into this summation function, and this summation function goes into this activation function, and finally after the activation you get an output y hat, right? So there are some, basically, yeah, in the bottom panel, if you see, there are like five important steps that you should remember. First is the input step. So, what is the input step? Input step is basically any input that you give. For example, let's say you give a cat image as input. Okay. So what happens, the computer actually stores your image, basically any image, as a sequence of pixels, right? So let's say you have a big image, and it is divided into, let's say, 4 pixels, 2 by 2. Your 2D image is divided into 2 by 2 pixels. You can imagine it as a matrix. Okay. So basically, there are total 4 pixels uh, in your input image. Okay, and then you pass that 4 pixels. So you will have 4 input nodes corresponding each input node corresponding to each pixel. So x1 corresponding to the first pixel, x2 corresponding to the second, and so on, x3, x4. Okay, and you get a separate term, separate node, which is called the bias node. If you see, it's marked in green over here. It's yeah, it's marked as, it could be marked as one, but this is just called the bias node. Okay, and so that is basically the input layer. Okay. Now coming to weights. So what are weights? So whatever weight you give, one easy way to think about it is that, okay, let's say W0 is will have some value, W1 will have some value, and W2 and W4. So if the weight for some particular pixel, let's say pixel 4, is more, that means your model will ideally give more weightage to that pixel when identifying that it is a cat or a dog, right? So, for example, let's say when you are identifying between a cat or a let's say a giraffe, right? Between two animals, cat and a giraffe. So what happens is that, one distinct feature is that cats have a, these whiskers around their nose, right? Whereas giraffes don't have those, right? So that could be one distinct feature. And let's say that those whiskers part is contained in a particular pixel, let's say pixel 4. Those features are contained in pixel 4. So what will happen if your model is good enough, it will train in such a way that it will give more weightage to that pixel, because that is a distinguishing feature between a cat and a giraffe. So it will give more weightage to that pixel, and in that way, the model will train. And in that way, it can identify whether this is a cat and a giraffe. Right? Is that example clear? So that is the significance of weights, right? Why would some input nodes have higher weights? Why would some input nodes have lower weights? Right? Now coming to sum. So what happens here is that, so every value of these input nodes. So okay. So when I was saying that, pixel, so your data is, let's say, your image is, let's say, divided into 4 pixels. So each of those 4 pixels, which will have their own uh, intensity. For example, bright pixels will have, higher pixel values. So the x1 value would be higher for brighter pixels, and similarly for, dimmer pixels, the input value would be lower. So these are called, values in RGB scale, red, green, blue scale. So if you have a redder pixel, the pixel value in R scale would be higher, and in green scale and blue scale will be lower. Similarly, if you have a greener pixel, it will have a higher value in green scale and lower value in remaining. Right. So that's the way it goes. Right. So okay, is it clear up to now? Inputs and weights. Is there any question? Okay. Okay. So the third part is sum. So what happens is that you just multiply the weights with the input values. So for example, W naught into 1 plus W1 into X1 plus W2 into X2 and so on. And you just sum them, right? So that's the idea. That's the sum function that is being represented over here. Just taking the weighted sum of all the nodes. And finally, after you take the sum, you pass it through this activation unit. So this is called, the yellow part is called the activation unit, right? So, I mean, you are very familiar with the sigmoid function. Let's say we have used it in logistic regression, right? So that could be one example of activation unit, right? So this is the step where non-linearity is getting introduced into the model, because this is not a linear function, right? So this is getting mapped into a sigmoid function. So if you remember, the equation for the sigmoid function is 1 divided by 1 plus e to the power of minus x. So it is a something of inverse of an exponential and something. It's not linear, right? And after that, you get the y hat value. So this part is similar to the logistic regression that we did. So whatever, so let's say if you get a value, your summation value, whatever you get in the summation value, if that value is greater than 0, the sigmoid function will take that value, and it will have a output of somewhere between, zero point 0.5 to 1, right? If you remember correctly. So let me see. So here is an example of a sigmoid function, right? So if your summation value is, let's say, on the right side, it will have a value between zero point 0.5 and 1. Similarly, if it's on the left side, I think it's becoming negative, but this side will be basically be positive, okay? And this side is negative. So if the summation value is positive, then it will take values between 0, 5 and 5. The sigmoid function will output a value 0. So yeah, so that is the basically if you see, okay, this is the nonlinear activation function, right? So if you see, this is basically the yellow step where you take the function of the summation, right? Okay, I think okay. So if it's not clear on Gmeet, maybe you can join YouTube Live. Okay, so I think in YouTube Live the texts are looking better. I think it's more brighter. Okay, it's in full screen actually, but I can let me let me see. Yeah, I think okay, okay. So yeah, is there any question on uh, till now, like the simple perceptron model? Okay, okay, then we can move on. Okay, now yeah. So basically, now what we saw is that given the way, uh, the question is how to find the weights. You don't know the weights from before, from prior to training your model, right? So how to find the weights? So that is a question. So if you remember, the method of finding the weights is simple. What we have already learned something, right? Like in linear regression, in uh, logistic regression, we have learned about gradient descent. Is there a question? Okay. Okay. If not, let's move on. So yeah, as I was saying, to find the weights, we'll do the same thing that we did in logistic and linear regression. We would you know do gradient descent on the weights. And simple, we will use basically, if you remember from linear regression, what we used to do is that weight in the n plus 1th iteration would be the weight of the nth iteration plus some learning rate times yi minus yi hat times xi. So again, so if you want to recall what we did in gradient descent, you can again go back to my YouTube channel and you can have some recall those uh, concepts. Actually, I have made separate small videos on gradient descent as well, so you don't have to go through the whole week's lecture. There could be like 10 to 15 minutes video on gradient descent with linear regression, where I have explicitly derived how the this factors comes in, right? So this is basically the derivative of the cost function with respect to your weight, right? So in general, the algorithm is this thing. The current the weight in the next iteration would be the weight in the previous iteration minus some learning rate times. If your error, if your cost function is simple least square error, then the derivative of the error with respect to the weight turns out to be this. Okay. And if you want to recall, you can go back to the linear regression part and and yeah, actually, this is basically the derivation. Okay, so this is how this derivative of the cost function with respect to weights comes in. So your cost function yi minus yi predicted. So this is actually the observed value minus the predicted value. Okay, let me zoom in. Okay, wait. In the meantime, if you have any questions, please let me know. Okay, right. So I think, yeah, yeah, I think Kavita is saying sigmoid activation function gives non-linearity for neural. Yeah, that's right. That's right. Right. So, okay. Uh, yeah. So as I was saying, the cost function is this thing within the brackets. So this is the yi observed minus yi predicted whole square, summation over all the examples, divided by 1 divided by number of examples. And if you take the derivative with respect to weights, so your yi predicted in case of linear regression is basically this simple straight line, right? Mxy equals to mx plus c. That is your straight line. So if you take the derivative with respect to the weights, which is in this case n, so this is how it turns out to be, and finally you get this thing xi times yi minus y predicted. So this is what we saw over here, right? Xi times yi minus y predicted, right? So this is how you update the weights uh, in case of a regression problem. Now, how to update the weight in case of a classification problem? So in classification problem, what you have is that so if you remember from logistic regression, if you recall from logistic regression, you will see that in case of classification problem, what we used to do, we used to pass the signal through a sigmoid function, right? So this is what we also do in our case also. We pass the signal through the sigmoid function. So this is still not being taken care of. So what we did till now is, we did till the summation function. If this would have been the end of our neural network, then it would be okay. Then the method of calculating the uh, derivative of the cost function is okay. But we have to pass the summation through the sigmoid function. And then what will happen if we further take this signal through, I will do now at my notebook. Okay. So let's see. So what we saw is that the error till now is this thing y minus yi minus yi hat whole square, right? So this is the cost function till now. But what we have to find is that uh, okay, so let me do mention some terminologies first. Let me draw the perceptron model again, right? So let's say you have this, and all this goes into this big part where you are getting summed up, and then this summed up is moved on to the sigmoid function. I will call this the activation function. Okay, so apart from sigmoid function, there could be other activation functions as well. So sigmoid function is one of the activation function. One other could be ReLU. Okay. So again, this is a homework for you guys. Go and look into all these different types of activation functions, right? So because in practice, when you are like implementing these models, sigmoid function is not very widely used. In fact, ReLU is a popularly used activation function. Another is soft plus function. Right? So you have to see what these functions are, right? So now I will, okay, you all know sigmoid function, right? The function is 1 plus e to the power of minus x, right? So this is the sigmoid function. ReLU function is, so this function is 0 if your, you know, x is less than 0. Whereas if x is greater than 0, then this is equals to x, right? So this function kind of looks something like, on the negative side, it's 0. On the negative side, it's 0. On the positive side, it's a y equals to x function. Okay? So this is the 0. Okay? So this is called a ReLU function. Another is soft plus function. The equation for this function is log of 1 plus e to the x. Okay, similar to sigmoid, this is the just the function. So we will see how to use sigmoid and soft plus function as our activation function. What will happen? What will change if we use soft plus function in case of sigmoid function? And yeah, so the final layer will get the output as this thing, right? So these are the weights W0, W1, W2, W3, W4, and these are my inputs. Okay, let's say X0, X1, X2, X3, X4. So here, what is my cost function? My cost function is summation of yi observed minus uh, sigma of w times x. Here I'm calling it w t, okay, whole square, right? So this sigma is basically the activation function that we're using here. So after you have like summed up all these uh, outputs, so what is the value that is going in this summation unit? In this summation unit, the value is going as w naught. Okay, this is x naught. This could be taken as 1. Okay, w naught plus w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. Okay, so whatever value, so this is in short written as w transpose x. So whatever value is going into this summation function, it is being transferred onto the activation function, which is represented by sigma. Then what you do is sigma transpose x. So basically this whatever w transpose x, it is getting transformed by this activation function. So if your activation function is sigmoid, so then it will be transformed as e to the power of minus w transpose x. If your activation, this is for sigmoid. If your activation is, let's say, soft plus, what will happen? It will be log of 1 plus e to the power of w transpose x. Okay? And so on. Right? Now, what we have to minimize here is this function, this j function over here. Right? And what we'll do is we'll do the same thing. We'll just, uh, take the derivative with respect to wi, right? So using chain rule, we'll do twice yi minus sigma of w transpose xi, right? Times, now we have to do uh, d sigma xi dxi, sorry, dwi, okay? Okay, this is, yeah, right? Okay, so we know how to, so this is again, earlier we have seen how to calculate this derivative. Okay, so how will we calculate this derivative? So we'll first, so let's say, let's consider two cases. First we'll do calculate this derivative for sigmoid function, and then we'll calculate this derivative for soft plus function, and we'll see what's the difference. Okay, so let me set this. Okay, So again, let me write the sigmoid function again. 1 divided by 1 plus e to the power of minus z. And this is the sigmoid function, and the soft plus function would be log of 1 plus e to the power of z, right? This is the soft plus. Okay. Okay. If we take the derivative of the sigmoid function, so let's do the sigmoid function first. Okay. Dash z would be e to the power of minus z divided by 1 plus e to the power of minus z whole square. Just taking the derivative of this whole term, right? So derivative of 1 by x is minus 1 by x square, and derivative of e to the power of x is e to the power of x, right? Similarly, yeah, so this will turn out to be sigma z times 1 minus sigma z, if you see, okay? Right? So if you just put the value of sigma z here, you will get the same term over here, okay? Now, what will be our derivative dj d omega I? So again, if we see from here, it will be twice of yi minus sigma w transpose xi times dj dwi, right? Sorry, d sigma dwi. So d sigma dwi would be, in the sigmoid case, it would be sigma of w transpose x into 1 minus sigma of w transpose x times, there will be a derivative of w transpose x with respect to w. That will be just be x. So this value is just x. Okay. So finally, what is dj dw? It's twice of yi minus sigma w transpose x times sigma w transpose x into 1 minus sigma w transpose x into x. So this will be xi's. Okay. And there will be a summation sign. Okay. Overall. Yeah. Right? Because we had the summation sign from the start. Okay. Right? Now, let's do it for the uh, okay, Mainak is asking, X is the set of inputs, right? Yeah, X is the set of inputs, and W transpose X is basically this summation function, W naught plus W1 X1 plus W2 X2 plus W3 X3 and so on. So that is just represented as W transpose X. Okay. Now, let's take the soft plus function. So soft plus function is log of e to the power of z. Okay. So sigma transpose z is 1 divided by 1 plus e to the power of z. Okay. Right. So I'm just taking the derivative of this times e to the power of z. Right. So derivative of log is 1 by derivative of log x is 1 by x. And again, derivative of e to the power x is e to the power x. I'm just applying chain rule over here. Okay. And similarly, the cost function would be summation over I twice of yi minus sigma w transpose xi times sigma transpose, sigma prime y transpose x times xi. Okay. So this is it. Now this will become, I'm just writing the same thing, and sigma dash w transpose x is e to the power of w transpose x divided by 1 plus e to the power of w transpose x times xi. Right. So yeah, this is the cost derivative of the cost function for soft plus function. And similarly, you can do derivative for other activation functions as well in similar way. So I have shown two ways. You should go and practice the the derivative for other activation functions. Is that clear till now? So after we obtain the derivatives, then what we do is we say that okay, the weight update step is Win minus some learning rate eta dj dwi. So this is the iteration that we do in our computer to update the weights until it converges. So this is basically the gradient descent. We have done it in linear regression, we have done it in logistic regression, and this is, uh, I guess, a little bit similar. Some differences are there, but this is how we do it for neural networks. The gradient descent concept remains the same. The calculations in between are a little bit different. Is there any questions uh, till now? Okay. If not, let me move on. All right. So we would see another interesting applications of this perceptron model, right? And after that, we'll go into, we'll add more layers and look into the full-fledgedly the neural network model. But before going into the whole neural network model, we'll try to see how we can build this logic gates using this simple perceptrons and maybe a collection of perceptrons, right? So, okay, so let me start with very, basic of logic gates and what could be their applications here. So, those who are from electronics background, they would electronics or electrical background, they would know this, Boolean algebra and those things. So these are heavily used in electronic circuits and uh, many other places. We'll see how they are, uh, relevant in neural network context. So let's say, so mathematically, you must have seen some truth table sometime uh, in your school or college. For example, so let's say you have two variables a and b, right? And so a and b could take any two values between 0 and 1, right? So if both a and b are 0, so yeah, one could be that both a and b are 0, another could be a could be 0, b could be 1, another could be a is 1, b is 0, and another is a 1, b 1, right? So if you simply construct an AND gate, so it just means that both has to be 1, then only the A dot B, this dot product would be 1. Otherwise, it will be 0. Compared to the OR gate, this is both, I mean, either of the two has to be 1, then only this one. Then only it is 1. If both of them are 0, then it's 0. Similarly, you can get NAND gates, NOR gates, XOR, XNOR, and so on, right? So NAND is just A dot B whole complement, and NOR is A plus B whole complement. So this complement means this bar over this thing means it's a NOT gate. So if A is 0, then what NOT does is just reverses the value. If A is 0, then A bar would be 1. If A is 1, A bar would be 0. So one way to think about this logic gates is you can think about this some as some machine. Okay. So let's say this AND gate is a machine. You give A and B into this machine, and according to the values of A and B, it will output you A dot B. Right. So for example, if A is 0, B is 1, it will output is 0. If A is 1, B is 1, it will output it 1, and so on. So these are something like machines which can yeah, which is basically uh, giving you some outputs, right? So that is mostly the theory between logic gates. Now we want to see the applied in our neural network models, right? So okay, so let's start with the simplest NOT gate. Okay. So let's say you have this perceptron model like this. So out of which this is the bias node, the plus one, and this is the input node. Okay. So there will be only one input node in case of NOT gate, right? Because if you see in NOT gate, you have only one input, A. Whereas in case of other gates like and OR, you have two inputs, A and B both. So NOT gate has only one input. So there is only one X1. And these are the weights that you have. Let's say 1 and minus 2. So then what will happen is that we'll do some calculations after this, but try to understand it from a conceptual point of view here. Is that what will happen to the summation function over here? So it will take 1 into 1 plus whatever input you give here times minus 2, then sum it up, and then pass it through the sigmoid function, and finally give you the output. So ideally, what we expect is that if x1 input we give as 1, the output should be 0. The weight should be such that if we give x1 equals to 1, the output should be 0. If we give x1 equals to 0, the output should be 1. So this is what we want, right, for our NOT gate. Similarly, for OR gate, here you see you have two inputs, x1 and x2, because you need both inputs, A and B, for OR gate. So similarly, you do the same thing. You sum up, multiply with the weights, sum of the uh, some of the results, and then you see the output. Here you would expect that if both are 1, if either x1 or x2 is 1, then you would get an output of 1. Otherwise, if x1 x2 both are 0, then you would get an output of 0. Similarly for AND gate. Okay, so this is how you expect this. Now the question is how to get the weights in this case. In this case, how did they get the weights 1 and minus 2, right? So we'll see how it happens. Now let me move on to my notepad. Okay. Okay. So let's say let's start with NOT gate first. Okay. So here you have the bias term, which is plus 1. Here you have the input, which is x, and then it goes into the summation function, right? And then it goes into the sigmoid function. Then you give the output y hat, predicted output. So before moving on, let me reiterate one property of sigmoid function that I already mentioned earlier. So this is how a sigmoid function looks like. Okay. So this is the 0.5 value. So this is value 1. So this is 0. So on the x-axis, you have your whatever the value you get from this summation function. This is y transpose x that we mentioned earlier. So this is the value you get. So on the x-axis, y transpose x. So this is the summation of w naught plus w1 x1 plus w2 x2, those things. So if you see, you see one thing that, okay, if my summation function, the w transpose x value is more than 0, right, some positive value, then your sigmoid function gives you an output between 0.5 and 1. So we can interpret that the output y hat is 1 in that case, right? Whereas if your w transpose x is less than 0, it will give an output between 0 and 0.5, right? So that in that case, the y hat would be 1. Sorry, 0. Okay. In the first case, it will be 1. So let me write it down here. So if W transpose X is greater than 0, then Y hat would be 1. If W transpose X is less than 0, Y hat would be 0. Right? Okay. Now, what we do, let's say, let us first, choose some random weights to the perceptron model. Let me first, give it as 1 and 1. Okay. Let's see what happens just as trial. Okay. So in this case, if we give an input of, let's say, 0 to X, okay, this is the input we are giving. What is the output that we are getting? So if we give 0, then our W transpose X would be uh, 0 times 1 plus 1 times 1. Okay, that is 1. So it is greater than 0. That means Y hat would be 1. Right? So that is correct, right? That we are getting the right output, right? Now, what will happen if we give W transpose, sorry, if we give the input as 1 instead of 0 here. Okay? So if we give it as 1, then W transpose X would be 1 times 1 plus 1 times 1, right? So that will be 2. Again, then W trans Y hat would be 1 because W transpose X is greater. Input as 1, the output should be 0, but we are getting Y hat equals to 1 now, right? So this is wrong, although the first case was right. Okay. So we have to choose the weights in such a way that, if we give 0, actually both the times we get the right out. So if we get input as 0, we'll get output as 1. If we get input as 1, we'll get output as uh, 0. So what we do is we, change the weights. So instead of taking, 1 and 1, let me change it to, let's say, what was given in the slide. Okay. So let's take the weight as 1 and minus 2. Okay. So here we just do minus 2. Okay. Instead of now W transpose X for if we take the input as 0. Okay. For input equals to 0, W transpose X would be 1 times 1 plus minus 2 times 0. So that would be 1. So W transpose X is greater than 0. That means Y hat would be 1. Okay. That is giving us the right answer. So if input is 1, W transpose X is 1 times 1 minus 2 times 1. So that is minus 1. So Y hat would be 0 in this case. Okay. So now in both the cases, it is giving us the right answer. Okay. So this could be one of the possible uh, you know weights that we can choose for our model. Right. Okay. Is there any question? Or should we move on to and OR gates? Right. Okay. Now let me move on to OR gate now. Okay. So here we have two input and one bias. So x1 and x2. It goes into the summation function, then it goes into the sigmoid function, then it gets the output. Okay. So here we calculate the W transpose X. So let's so what do we want? So if you don't know the weights from before, from earlier, the one good way to look at to construct this, you know, network is that what we want. Let's draw the truth table first. So that's one way to go. So 0, 0, 0, 1, 1, 0, 1, 1, and x1 or x2. So this will give you 0, 1, 1, and 1. Okay. So what we want is that if either one is 1, so if x1 or x2, any one of them is 1, then we want W transpose X to be greater than 0, right? And if both are 0, then we want W transpose X to be less than 0, right? So let's consider the first case first. If both are 0, then we want W transpose X to be less than 0, right? Okay. So if both are 0, you see that this weights W1 and W3. Let's call this W0. Okay. So sorry, W1, W2. W0, W1, W2. These are my three weights. So if both are 0, you see that W1 into 0 and W2 into 0. It will be 0 completely. We don't need to worry about those. What we need to worry about is W0. This is the only weight remaining if both are 0. So what we want is that W0 to be less than 0. Okay, got it? So let's set it to a negative value. Let's call it any random negative value, minus 30. Okay, now we'll fix. Now this condition is done. Okay, now let's move on to the next condition. Next condition is that if either, let's take next two conditions at once. If either x1 and x2 are 0, sorry, x1 x2 are 1, then we want W transpose X to be greater than 0, right? Because y hat has to be 1. Okay. So how do we fix now W1 and W2, right? So if let's say 1 is 1, so let's say x1 is 1 and x2 is 0. So what should be W2? W2, we can fix it as some value which is higher than 30, right? If we set it at some positive value, so one thing is for sure that this summation has to be positive. So W0 plus W1 x1 has to be positive. So sorry, let me do it. Let me restate my statement. So in this case, if x1 is 1, x2 is 0, right? We are talking about this case now. Okay, this one. Okay, if x1 is 1, x2 is 0, then what is my W transpose X? W0 plus W1, right? We have already fixed W0 as minus 30. Now we want this summation to be greater than 0, right? So what we will do, we'll set W1 as some value greater than 30. Okay, only then the summation will be positive, right? Otherwise it will be negative. So we set W1 as, let's say, 40, right? Similarly, if you look at this case, you can also set W2 as 40, right? And this automatically satisfies the third case. If both are 1, then obviously W transpose X is greater than 0, right? So this is one possible combination. W0 is minus 30, W1 is 40, W2 is 40. So this is one combination. There could be other combinations as well. Minus 3, 4, 4 could also be another possible combination. I'll explain what are the physical differences between those two combinations, right? I'll explain it in a minute. But is there any question? Do you now understand how to construct this networks using the truth table? So, again, to reiterate, first step is to construct this truth table. Look at this truth table. Okay. Second step would be construct this uh, perceptron model. So once you have this picture, drawing a picture is very helpful in this case. Once you have this picture, you can see, okay, this is my bias node, this is my x1, x2 node, and so on. And then it becomes very clear. Then step 3 is to go through the logic, this truth table, one at a time, step by step. As we saw the first case, when both are 0, Then we fix the weights. We could fix only W naught. And then we went to the next row of the truth table. And then we fix W1. Then we go into the next row. We fix W2 and so on. This is the stepwise. You can go through the truth table and find the weights. So this is one way. Now, is it clear? Can you now construct any logic gate using this method, using perceptron model, right? Similarly, you can do it for AND gate, right? Can you do it, or it's still not clear, right? Okay, okay. Monica is asking how weight values. So weight values are not given. Weight values are the values that we have to calculate. Okay, I will explain it with AND gate. Okay, now I will explain it with AND gate. Okay, let's see. So weight values are the values that we have to calculate. Okay, we'll go step by step this time. So step one is to write the truth table. So x1, x2, and then x1 dot x2. Okay. So if x1, x2 both are 0, then it's 0. x1 is 1, 0, 0, 0, 1, 0, 1, 1, 1. Right? This is step one. We construct the truth table. Step two, we draw the perceptron model now. So this is the bias node, x1, x2 node. x1 node, x2 node, bias. Right? This is the summation function. These are the weights W0, W1, W2. Okay. Summation function moves into sigmoid function, then you get the output y hat. Right? Okay. Is that clear? Now, step three is you go through this your truth table one by one. Okay. So step three. So let's look at the first row of the truth table. So first row says that if both are 0, then your output is 0. Okay. So if both are 0, so if x1 and x2 both are 0, okay. So let me, okay, yeah. I think now it's visible. Okay. Let me draw the truth table again here. x1, x2, x1 times x2. Okay. 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Okay. So this is the truth table for AND gate. Now we'll go through the truth table one step at a time. So the first row is if both are 0, then we should get the output as 0. So in order to get the output as 0, we need to have the summation to be less than 0, right? So if the summation is less than 0, then W naught should definitely be less than 0. So let's fix W naught to be again, let's say minus 30. We can fix it as some negative value, right? Now, this is the first row is done. Now coming to the second row. So if x1 is 1, x2 is 0, then what is the summation sign? My summation would be W naught plus W1, right? And W2 X2. W X2 is 0, so W2 X2 is 0. Okay? So this should be uh, 0, negative, right? So what we do is we choose W1 as some negative value, let's say minus 20, right? Sorry. Wait a minute. The summation has to be negative. W naught plus W1 has to be negative, right? Doesn't mean that W1 has to be negative, right? Um, Actually, equal to 0 is a very, it's not well defined actually. When it's equal to 0, what happens if you remember the sigmoid function when y transpose x is 0? So it is not well defined as that. But, coming to a question, uh, W transpose x, uh, I mean, if your sigmoid function gives a value of 0.5, you can manually define it as to be taken in the y hat equals to 0 category. Or you can do the other way also. You can 1 category. Because you see, the value 0.5 is exactly between 0 and 1. So it's up to you which you want to choose, whether you want to take the y hat equals to 0 value or you want to take the y hat equals to 1 value. So I'm not going into that ambiguity, but in general machine learning models, getting these weights are, these weights are so fine tuned that you would rarely get a value 0. So it will be some, even it's very close to 0, let's say minus 0.0000 dot 0.0005. Let's say 5 decimal places after something, some value you will get out of this, right? Exactly equals to 0, it's very rare, right? And if it's 0, I think the machine overrides it to some value, y hat equals to 0 or y hat equals to 1. Yeah, I am saying that, right. Yeah, so I am saying that if you take the equal sign, so what will happen if W transpose X is equals to 0? If W transpose X is equals to 0, your sigmoid function, after you run it through the sigmoid function, it will give you a value of zero point 0.5, right? Now for if the sigmoid function value is zero point 0.5, what will you do with y hat? Will you call y hat as 0 or will you call y hat as 1? It is ambiguous, right? You could call y hat as 0 also, you could call y hat as 1 also, because it is exactly in between 0 and 1, right? So I'm saying it's very rare that you will get an exact value equals to 0 in actual practical cases. And if you get y hat W transpose x equals to 0, then the machine could make y hat equals to 0 or it could make y hat equals to 1, right? Forcibly. So if you take the y hat less than 0 condition, then it's okay. You can take it, or otherwise you can also take greater than, with the greater than also you can take the 0 value, right? So I'm saying exactly equals to 0 is very rare. You would not get the value equals to 0 exactly. So we can, for now, we can neglect those cases. Okay. So, okay. So where was I? Okay, I was explaining the second row of the truth table. So if x1 is 1, x2 is 0, so this is the summation you have, and you want to get you know w naught plus w1 less than 0. So what will happen if I take w1 to be 20? So then w naught is minus 30, w1 is 20, then it's minus 10, right? Which is less than 0. So it satisfies the condition, right? Okay, it's not visible. Let me see. Okay, yeah, this will. So as I was saying, if you take W1 to be 20, then W naught plus W1 would be minus 10. which satisfies the condition, which is less than 0, right? Similarly, you know, now let's come to the third row of the truth table. Okay, this row. So what will happen is that if you take the summation, so that means x1 is 0, x2 is 1. So that means the summation will be w0 plus w2. We want this to be less than 0 because the output y hat has to be 0. So w0 is minus 30. Again, we can take w2 to be 20. Then it's minus 10. Then it's less than 0. Right? It satisfies the condition. Right? Now coming to the last step. So this is when both are 1, then that means the summation would be w0 plus w1 plus w2. So that is minus 30 plus 20 plus 20, it's plus 10. So that is greater than 0. So this automatically satisfies the condition. So if we take the weights as minus 30, 20 and 20, then it satisfies all the conditions of the AND gate. And thus we construct the AND gate. Okay, is it clear now? Okay, now I guess now it's a homework for you guys to construct other gates like NAND, NOR, XOR, XNOR using this truth table. And yeah, just as we did for AND and OR gates, right? Okay. Now coming to neural networks. Okay. So this is now we are moving ahead of the simplistic perceptron model that we had. Now we are going into a full-fledged networks of neurons. Okay. Earlier we had only one node. Sorry, not one node, but basically we had only one layer. If you see now, if you look at the right picture, okay, what is happening here is that you have this inputs. So yeah, this was the earlier model. Okay, so this if you see on the small dotted square within the square, if you see, this is the model that we had earlier, right? Now what will happen, we will take this model and we'll insert this model into each of these circles that you see. Okay, in all these circles is this connected perceptron. Okay, and you can have layers of many of these neurons, artificial neurons, and you can make layers of these neurons. You can take multiple neurons and make a layer out of it, and you can have multiple layers as well. So the information from one layer is propagating to other layers and finally giving you the output, right? So this is a whole neural network model that you see. So initially you give output into the nodes, right? And then it goes into this small perceptrons or neurons that we see. These are called hidden layers. Okay, so you could have layers of these multiple neurons, and you can have multiple layers one after another. See, and finally which goes into the output. Okay, so this is the input level, and then you have multiple hidden layers, and finally you have the output layer in a well connected fashion. So this is what an artificial neural network looks like, right? So we started with a simple perceptron model, and we went on to make a networks of this model using layers of this individual neurons, right? Now I will explain like how information propagates, how the input, when you give an input, how it gives you an output. So I will explain it with an example first. Okay. So let me uh, let me explain what this problem is. So let's say again, if we say that okay, we have some medicine and we want to see which is the optimal dosage of this medicine which gives good results, right? For example, in this case, this is zero dosage. So if you get zero dosage, obviously you will get no output. So basically, it doesn't work. That means the output is zero. So if you take medium dosage, let's say this dosage is 0.5, then yes, okay, this medicine is working. Okay, your output is 1. If you take dosage equals to 1, very high dosage value equals to 1 mg, let's say 1 mg of some medicine, then again, your medicine doesn't work, right? So this is the example. Now you see that, one limitation of this perceptron models was that it can fit only linear functions. Okay, it couldn't fit uh, this non-linear curve that you see here. What we need to fit is that this non-linear u-shaped curve, right? So that for very low dosage your probability of this medicine working should be very low, whereas for this medium dosage your probability of this medicine working should be high. This is what this nonlinear curve is what we want, right? We don't because no linear function could fit our data, right? So for example, if we draw a linear line like this, it couldn't fit because it would say, okay, this is the positive, this is the negative, but that's not the case. So we need a nonlinear curve to separate the positive samples from the negative samples. Okay. So Menak is asking, each of the nodes in a neural network is a perceptron. Yes, that's actually correct. Each of the nodes is a perceptron. Because you see, for this node, we are getting inputs from all the input nodes in the previous layer, right? So similarly, as we see for a perceptron, we are getting W transpose X, which is getting summed up and passed through a sigmoid function, and then you get the output of that node. Similarly, each node is getting inputs from all the input nodes, and it's getting summed up and passed through a sigmoid function, and you get the output, right? So it will be clear if I, go through this example. Okay, this is the example that I will show. So what will happen? This is a very simple example to uh, fit this data. But using this example, it will give you an idea. So you could have multiple, more complex nodes and more complex layers. So this is a simple. We have only one hidden layer in this case. This is the hidden layer. You could have multiple hidden layers. Also, in this hidden layer, we have only two neurons. You could have multiple neurons as well in the first hidden layer. Okay. But this is the most simplistic example of a neural network. So this is a one step higher than the perceptron model that we saw. I'll just explain what will happen. So let's say you give your input here. So your input is, let's say, first input is 0. So if you give the 0 input, what will happen? It gets multiplied by this weight. Okay. So this weight is 3.34. So 0 into 3.34 plus it will get added to this bias term. This is called the bias term, like we had in the perceptron model, right? We had this bias. So 0 into 3.34 plus this bias is minus 1.43 plus this. And then what will happen after the summation? It will go into the activation function. So in this case, we are taking the activation function to be soft plus. This is log of 1 plus e to the power x. So whatever the summation value, it will go into log of 1 plus e to the power of that summation value. And the output that you get, that is again getting multiplied with minus 1.22. And then again, you are getting summed up. So same thing, you do it in the bottom connection. Okay. In this bottom layer, you do the same thing. And then whatever output you get, you sum up the results from both the layers, both the panel, top panel and the bottom panel, and then you add 2.61. This is the bias term again, and then you get the output. Okay. So this is how you get your output. So what will happen actually if we give the input as 0? We should expect an output of 0 as well, right? If we give the input as 0.5, so this is respect to the dosage 0.5, we should expect an output of 1. If we give the dosage as 1, input is 1. After doing all these steps, the output should be 1. Okay. So I will quickly do this calculation. Okay. Let me go to my notebook. I'll quickly show you for one case, for one input, I will show you, and then we will see. Okay. Okay. So Let me first draw the network here. This is the input node 3.34 minus 1.43. So plus, okay. So I have drawn the network. Okay. So yeah, let me see how it goes. So if let's say your input is zero in the first case, okay, your input is zero. So what you do is you pass this input through this layer. So for dosage zero, dosage equals to zero. For the first layer, if you go from this thing, let's call it A, and let's call the bottom panel to be B. So if you go through the A first, so your network will first multiply it with 3.34 and then add minus 1.43. Okay, so this output is minus 1.43. Okay, now what it will do, it will do the pass this 1 point minus 1.43 to a to the soft plus function, and the equation for soft plus function is log of 1 plus e to the power of this summation thing 1.43. Okay, so if you calculate this, we'll get value 0.22. Okay, right? All right. Now, uh, okay. So this is here. It gives an output of 0.22. Now you multiply 0.22 with uh, minus 1.22. So here you get an output as minus 0.27, right? So up to this, you have output minus 0.27, right? Similarly, if you go through the same step in the bottom panel, here your output would be uh, minus 2.35. Okay. Now what you do is sum these two. Okay. This summation, it will do minus 0.27 minus 2.35, right? And then again you have this another sum which is plus 2.61. So if you calculate this, it will come out to a value very close to 0.01. So this is your output, right? So if you, okay, let me see, it's not visible. Okay, now it's visible. So this is the minus 0.27 is from first layer, the top panel, and this is the value from the bottom panel, 2.3 minus 2.35, and this is the 2.61 that you have to add this term, okay, and you get the output very close to zero. So what we see is that if we give input equals to zero, our output is also equals to zero, right? Similarly, you should check what if you give an input of 0.5. Okay, so let me, yeah, let me tell you. So all those which I have, marked in box, which I have made a box in red, those are the bias term, and the all those which are shown with black circles. So these terms are the weights, right? So these four are the weights: 3.34, 3.53, 1.22, 2.3. These are the weights. Whereas the red ones are the bias. So weights have to be multiplied and summed up with bias. Is that clear? Okay. So like that, 0 times 3.34, what we did here. So input is 0 times the weight we multiplied plus the bias. Okay, here. And then we get the output, passed it into this activation function. Whatever the output of the activation function, we multiplied it with weight, which is minus 1.22, and then we get this output. We then sum up with the output we get from layer B, and then add it with the bias to get the final output. Okay. So this is the step that you do. Similarly, you can check for input equals to zero point 0.5. For input equals to zero point 0.5, you should expect an output equals to 1. Whereas for input equals to 1, you should expect an output of 0. Right? So this is how a neural network works. And you can, similarly generalize it if you have multiple layers and, multiple nodes and so on. Right? You can make it a more complicated thing and, but the calculation remains the same. Right? Now, okay. Now the question is, how do you calculate the weights? So you see, similar to the what we encountered in the perceptron model, here also we have to calculate the weights, right? So that is the question. So before going into deep into weights, uh, I just want to recapitulate a thing about chain rule. Okay. So I think many of you would know about this, but this is something that we will use while calculating the weights in this back propagation. So what is chain rule? So if you have uh, some which is actually a function of another function. So y, this is a function of another function which is g, right? How do you take derivative of y with respect to x? So first you take derivative of this f with respect to gx, and then you take derivative of this g function with respect to x. Okay, so this is a way of saying it, that if y is a function of u, and then if u is again a function of g, okay, then what you do is, if you want to take the derivative of y with respect to x, you take the derivative of y with respect to u first, and then you take the derivative of u with respect to x. Okay, so this is the way to just give you a quick example. Let me go to my notepad. Okay, so this is a very basic rule, but I want to make sure that everybody understands this so that it will be easy if when going forward. Okay, so okay, so just to give you an example of chain rule, if let's say your y is a function of I don't know, let's say sine of x square. Okay, so this is a function. Okay, or let's consider a simpler function. Okay, let's consider e to the power of something, e to the power of ax square. Okay, so this is a function. So what will be dy dx? Okay, so first you take the derivative. So you consider ax square to be one unit. Let's say z. So first, what you do is you take the derivative of y with respect to you see z, and then take the derivative of z with respect to x, and you multiply it. So y with respect to z would be this is e to the power z. Derivative of e to the power z with respect to z is e to the power z times derivative of z with respect to z. Z is ax square. Derivative of ax square is 2ax, right? So this derivative becomes e to the power of ax square, right? So this is a simple example of chain rule. Okay. Okay. So if anybody didn't understand this, let me know, because we are going to use it uh, in this back propagation. Okay. Okay. So what we do, so initially, just like in linear regression and logistic regression, what we did, we would use the gradient descent method. Okay. So in gradient descent, what we do is we first initially choose some value of these parameters. And what are the parameters here? The parameters are weights and biases. So let's say this weight is W1, B1, W2, B2, W3, B3, and so on. So we want to get the optimal values of these W's and B's. Okay. Okay. Prerna is asking, can you explain the? Uh, okay. So which part here? So what we do is that we first take the derivative of exponential first. So if y equals to e to the power of ax square, we first take the derivative of exponential. So so what we do is that so y is e to the power of z, right? And z is ax square. Okay. So first what we do is dy dz. It's e to the power of z because e to the power x derivative is e to the power x. Okay. And then what we do is we calculate dz dx. dz dx is 2ax. So x squared derivative is 2x, and we have this a term which is a constant. A is basically a constant. So dz dx is 2ax. So we multiply ez in times 2ax, right? And z is again ax square. So we just substitute z with ax square. So once you get habituated to this, the quick way to think is that, if we have y equals to some function, let's say another, I will give another example. Let's say sine of ax square, okay, instead of e to the power of sine. So you first, to calculate dy dx, you first calculate the derivative of sine. Derivative of sine is cosine. Cosine of ax square times derivative of ax square, that is 2ax, right? Simple. So if you have first function, you just go one by one. That's why it is called chain rule. You first take the first part and then multiply it with the derivative of the function, the second part. Okay. So the first part is sine. So derivative of sine is cos, and then you go into the function within the sine, that is ax square, and then you take derivative of that function which is within the sine. Okay. That's the one way. That's the way to go. Okay. I think you can practice with a lot more examples. I think then it will be clearer. But now coming back to the back propagation algorithm. So here what we do is arbitrary value of these weights and biases, which we have to optimize, using gradient descent method. So and how we update these values, that is basically the back propagation algorithm. So first, the initial choice of W1 is, let's say, 2.74, is minus 1.13, W3 is this, W4 is this, and so on, right? And these are the bias. Okay. So what could be the initial choice of bias? Generally, people choose 0, okay, at first, and then they update the value of bias. We'll see how we update it. Okay. So you can update the bias B1, B2, B3 as 0, and you can update this W1, W2, W3, W4 as these values. You can choose other values as well, and then you can apply gradient descent. So basically, we just choose some random values, and then we apply this back propagation algorithm. So what is this back propagation algorithm? So you see, you initially, after you chose some initial values of these parameters, you give this input as something, and then you get an output. Now, let's say your first input is value 0, dosage equals to 0. Whatever output you get, let's say you don't get a output value very close to 0. So unlike we saw in the previous case, like if you get a output value of 0, but you see you don't know that these weights from before. So what you do is you start with this random weights, and then you see the output. So let's say the output in this case comes out to be some value zero point 0.6 or something. So then what is your error? You look at the error. So error would be sum of square residuals. So this is same as what we did earlier, right? Y minus y hat whole square. That is the sum of square residual. Also in short known as SSR. Okay. So now you have to optimize this SSR. You have to do the gradient descent algorithm, right? So in order to optimize this SSR, you have to take the derivative of this error function with respect to these parameters, and then you update these parameters. For example, let's say you are updating B3. So what you do, B3 in the next iteration would be B3 in this iteration minus derivative of SSR with respect to B3, basically this term, d of SSR by dB3 times some learning rate, right? So this is basically just this formula that we were yeah, this one on the right. So in this case, just replace W by B3. So B3 new weight would be B3 old weight minus some learning rate times derivative of SSR with respect to B3, right? Now here it's become more complicated than a perceptron model because here you have many other networks. And so in order to calculate the derivative of SSR with respect to B3, you need to apply chain rule. Okay. So what is the derivative of SSR with respect to B3? So I'll do this I'll do this calculation in the notebook. Let me uh, do it here. Let me open a new notebook. Okay. So here we'll study back propagation. So we'll do the whole calculations and everything step by step. So just uh, bear with me. So what is SSR? Sum of square residuals or the cost function is summation over I. So in this case, I is 3. We have 3 examples if you remember. Dosage 0, dosage 0.5, dosage 1. So I'm just looking at this example. I think it will be easier. So we'll get the observed value minus predicted value. Okay. Square. Okay. So this is the least mean square thing that we're getting. Now, what is the predicted value here? So let me again draw the network. Okay. So in the meantime, you think about the forward propagation algorithm, right? How do you get the predicted value in terms of these weights? Okay. So how you get is you multiply the input with W1, add B1, and then perform this transformation Y1 equals to f of x1. Here f is your soft plus function log of 1 plus e to the power x. And then you multiply it with W3, sum it up, plus B3, uh, and then you will get the output, right? Okay. Okay. Let me go back here. Okay, so this is what you do. You give your input 1 plus b1, pass it through the sigmoid function. So after you pass it, let's say the value is w1 y1, sorry, y1, multiply y1 with w3, add it with y2 equals y2 times w4. Similarly, you do the bottom panel y2 times w4. Okay, right? So multiply with w1 plus b1, you get y1 after passing it through the soft plus function. Multiply y1 with w3, add it with y2 times w4 plus b3. Okay, and then you get the output. That is the predicted value. Okay, so what is the predicted value? Your predicted I is y1 w3 plus y2 w4 plus b3, right? Is that clear? And here your y1 is f of x1, y2 is f of x2. Similarly, x1 is w1 into input I plus B1, x2 is W1 into input I plus V2. Sorry, W2. It will W. So x2 is basically after whatever value you get after this. Okay. So x2 is basically input times W2 plus B2, and then you get x2, you pass it through the function, you get y2, y2 times W4 plus this plus B3, you get the output, right? Is that clear? So here, this is very important, right? So how you get all these things, it will help us in deriving the derivatives, okay? So now let's start with the first thing first, okay? So let's do one by one. So what we need is derivative of SSR with respect to B3. So first, you take derivative of SSR. So this is the SSR formula that we wrote. So first we take the derivative of SSR with respect to derivative of predicted. And then you take the derivative of predicted with respect to B3. So what is derivative of SSR with respect to predicted? It's simply twice observed minus predicted. Okay. Derivative of x square is 2x. That's it. Times derivative of predicted in terms of B3. So you look at this expression. So you see where is B3? B3 is here. Rest y1, w3, y2, w4, these doesn't depend on b3. So all the derivative of these terms will become 0. Only the derivative of b3 with respect to b3, that is just 1. Okay, derivative of b3 with respect to b3, that is just 1. So we just get twice of observed minus predicted. Okay, is that clear? Right? Now we'll step it up a bit. Uh, similarly, derivative of SSR with respect to, okay, so once you obtain this, B3, you just do what you do is you update the B3 in the next iteration equals to B3 in the first iteration minus some learning rate DSSR DB3. Okay, so whatever value you get over here, you whatever value you get here, okay, you input this and then you update B3. Initially B3 is 0. So it will next in the first iteration B3 will just be eta learning rate times this thing, whatever observed minus predicted you get. Okay, great. So I will calculate one value for one value at the end. But before that, let me calculate the derivative of SSR with respect to W3. So derivative of SSR with respect to W3 is again derivative of SSR with respect to predicted times derivative of predicted with respect to W3. So if you see from here, derivative of predicted with respect to W3 is just y1. Okay, this value y1. Okay, remaining terms doesn't depend on W3. So derivative of SSR with respect to predicted is similarly derivative 2 into observed minus predicted times y1. Okay, this is it. Now, a little more difficult is to take the derivative of SSR with respect to, let's say, W1. Okay, so what will be the derivative? So now what will happen? Derivative of SSR with respect to derivative of predicted times derivative of predicted divided by derivative of W1, right? So, but you see here in the predicted, you don't have W1. It's Y1, W3, Y2, W4 plus B3. So what to do? But you see this Y1 is a function of X1 and this X1 is a function of W1, right? So what we do is we take derivative of predicted with respect to Y1, and you see this y1 is a function of x1. So derivative of y1 with respect to x1 times derivative of x1 with respect to w1. right? This is where the chain rule comes in, right? Can you guys see this? Okay. Can you guys understand this, right? So again, similarly, D of SSR with respect to predicted is twice observed minus predicted. Derivative of predicted with respect to Y1 is W3. If you look at here, derivative of predicted with respect to Y1 is W3. Now derivative of Y1 with respect to X1. So what is Y1? Y1 is f of X1. In this case, we are using the soft plus function. Soft plus function is log of 1 plus e to the power x1. So derivative of y1 with respect to x1 is equal to 1 plus e to the power x1, e to the power x1, right? E to the power x1 divided by 1 plus e to the power x1, right? So we put here e to the power of x1 divided by 1 plus e to the power x1. What is the derivative of x1 with respect to w1? So if you see this here, it's just input I times input I, right? So this is the derivative. So this is what you should understand, right? Can everyone understand this? This is important, okay? And similarly, you update the W1 parameter by using gradient descent, just like we did for B, okay? Similarly, W1 would be I plus 1 equals to W1 I minus eta of TSSR dW1. So this is how you do it. Similarly, you do for all the other steps, W2, B2, B3, B4, so on, right? You take the derivative and then you update those parameters. Okay. Okay. So let me just do one example. So if I take, let's say, input as 0, the first value we do, okay, and we pass it through our initial gradient descent, initial this model, whatever weights we choose, 2.74, this, and so on, we pass it through it, okay, and we get the output as which is the predicted value as 0.68. So again, by this is by forward propagation. We did the whole calculation earlier. So if you should calculate this again, and you will get the output as 0.68. Now you see what is the observed value. This is the observed. This is the predicted, right? So this is your observed value is 0. Predicted value is 0.68. So if we are to calculate, let's say d of SSR with respect to B3, okay, this is twice into observed minus predicted. So what will it be? This value would be twice into 0.68 minus 0, right? That is 0.136. Okay. So D of SSR with respect to B3 would be twice into observed minus predicted. Okay. So there is actually summation sign. Okay. Summation sign. You have to sum over all. Here we are only taking the first input. So what you do is you put the second input, that is dosage value 0.5, and then again you calculate the predicted value, which should be something different, and again you calculate for the third input, that is dosage value 1, you calculate, and for all these values you will have some observed value and predicted value. You subtract them, multiply it by 2, and then add them all up, and that is the value of D of SSR of B3 that you get. And finally you update then B3 after that, and then you do time, right? And then you update all the parameters, and finally you get your neural network. Is that clear? I will stop for 1 minute. That sink in. In the meantime, if you have any questions, let me know. So after this, we will just do one part, which is deep neural networks. Okay, and then we'll do some hands-on. So we'll cover this quickly, and we'll cover most of it through hands-on only. So So you see, these are what happens is that this is the this deep neural network is very vast and it's a very vast topic, and these are totally cutting edge research that are going on, and there are a lot of models and people are trying to develop each and every aspect of it. So what are the disadvantages of the artificial neural networks that we saw? One is the diffusion of gradient. So when you have lot of layers and lot of nodes, your gradient update algorithm will become very slow. Your gradient descent will become very slow. And that's why you will have slow convergence due to huge number of input nodes. Okay. So there are few, solutions to this. One is autoencoders, which is shown via this uh, picture, if you see here. So what is happening in this? If you have to train a lot of nodes at once, your model will become slow. So what you do is you train one layer by layer. Okay. So let's say you train the first hidden layer and then you go on to the second layer and so on. So you train one layer by one. So in this case, what you do is you give your input a little bit different output with some noise, added noise, and so on. Right. So this is what an autoencoder is. So your input is same as the output, and in the meantime, your hidden layer, that is the bottleneck, would be a layer which has a lower dimension than the input, so that it can learn only selected features from the input. For example, if the example that I was saying at the beginning, that a cat, you have a cat, you can identify it with a giraffe with respect to its nose or its whiskers around it, right? Or some other features like the hair on the cat, right? Uh, and so on, right? For example, if you have to differentiate between a cow and a cat, so though cows have hooves, so in the legs, so you can differentiate from the legs, whereas cats have claws. Cows don't have claws, and so on. So claws is could be one of the features that is being captured in this one of the hidden layers. So you don't have to capture all the features of the input. You capture only the selected features which are being captured in this hidden layer of this autoencoder, right? So that's why you have this reduced dimension in the hidden layer, right? So this is an example of autoencoder. We'll see in detail once we do the hands-on. This is a convolutional neural network. So what happens is that you have an input, you convolve that input with some filter, and then you move the filter, you do some pooling. I'll explain what this pooling means, and then you do pass it through an activation unit like ReLU or softmax, as I said, and then again you do pooling, and finally you flatten the data, and then you, after flattening, you put the input through the conventional neural network, this fully connected neural network, and finally you get the output. So what happens is that in this, what happens is that if you have a high dimensional data. Let's say if you have an image, so image could have multiple pixels, right? Many pixels. So what you do initially, if you have to go through the conventional neural network methods, like sorry, not conventional, like the artificial neural network method. So what you do is you take the pixels, take all the pixel, you put it in a row, put it in a column vector, and then you give the input as that, right? And then you pass it through all the hidden layers, and then you get the output. But you see, if you have a big image, you have a lot of pixels. It's not possible to give all those pixels an input. It will complicate your layer. So what you do is you filter it out. You do a convolution so that your data is reduced to a lower dimension. So that is what, and after that you fit the lower dimensional data into the neural network. So that is what is being happening in the right side over here. And this is the process by which you reduce it into a lower dimension. So I'll explain a little bit while you do the hands-on of this, how we reduce it. And this is the bottom panel. This is the recurrent neural network. So what happens here is if you have a continuous data, like for example, stock data, right? So if you have stock prices that is varying every day or every second. So how do you predict what will be the value tomorrow? So by knowing the value, of the previous day and today, you have to predict what will be the value tomorrow. So in this case, what you have to do is that your model is getting continuous input. So instead of so what you do, you take the input of today's value, and then you take the input of yesterday's value, and then you make a feedback loop and input it into the model, and then again you input the today's value, and then you predict the tomorrow's value, and so on. So this is a feedback loop. For example, if I go through this picture. So let's say you know the today's value, right? But okay, let's look at this picture. So x t minus 1. So t minus 1 is yesterday's value, one day prior value. X t is today's value. And this is the x t plus 1. That is what you have to predict. So you input the previous day's value and the today's day's value, and using those two, you predict the tomorrow's value. So again, I will show how we do this using the hands-on. So let me go to the exercise first. Okay. So, okay, first, let's do the autoencoder part. So, this is just importing libraries, and this is the autoencoder. And yeah, is there a question? Okay, okay. Is it visible now? It's okay, right? So, if you have gone through the lectures of this week, the MNIST dataset is the dataset which contains images, right? So, if you see, they have written 1, 2, 3, 4 in different ways. So, the output classes are basically 10 classes from 0 to 9, right? And, you give your input to the data, and your output should be, so let's say you give the image of 1, predict that, okay, this is 1. This is the value 1, not any other value. So that is the thing that we want to do. Instead of, predicting, so if you see, okay, this thing. So this is the first row, if you see. So this is the original images that we are giving to our model. For example, this 7, 2, and this is the images that are being generated after it has been passed through the autoencoder step. So if you see in the slides, so the first row represents the input, like the original data, which is giving as input. And the second row is the encoded data, which is being represented by the hidden layer, by this first hidden layer. So if you see, there are slight differences dimensionality reduction that is happening over here. For example, if you see this 7, so this 7 is very smooth, whereas this 7 is little bit smudged. And why this blurring takes place is because you have a lower dimension, lower number of pixel, lesser number of pixel to represent the data, right? But it works. Even the lesser dimension, the lower dimension works pretty well, right? So since you don't have such high computational power, you want to reduce your data to lower dimension using this autoencoders, and this is the lower pixels that you see. These are the uh, you know encoded images that you see. So if you see here, I will post this notebook, but you can practice with it. So if you see latent dimension, so this is the dimension 64, right? So you get the original dimension. So your original dimension would be, I think 28 cross 28 pixels. So that will be around 784 pixels that you have. Okay. So in the first input layer, what goes is this, you have 784 nodes. So after that, you have reduced it to 64 nodes. So instead of the 784 pixels, you just have 64 pixels in the hidden layer, right? So, okay, so this is the latent example, and this is the loss function, which is the mean squared function that we are giving. You can choose other loss function as well. This is the Adam optimizer, or yeah, so this is one of the optimizers that we use, and we have trained this model with 10 epochs, and this is the batch size, okay? And then we are seeing the output. Okay, so this is the result. The bottom panel is the result with uh, the encoded images, and this is the original image top. So okay, so why? Okay, let me explain a little bit about epochs, batch size, and iterations. So what are epochs? So let's say you have data. Let's say you have 10,000 images. So your data is 10,000. Okay, and you want to train your model with this 10,000 images. So what you do, you just don't push the data off at one time only. So what you do is that uh, you push 10,000 data, you train your model, backpropagate the errors, and you refine your weights, and you get the final weights. That is one epoch. And then you repeat this process again and again. Okay. And this is the number of times you repeat it is the number of epochs. So we are repeating it 10 times here. Okay. And batch size. So what is batch size? Batch size is in one batch, how many data samples you want to push, right? For example, in one epoch, so let's say your data size is, as I said, 10,000 images that you have. So in one batch, you put 256 images, right? And then in the next batch, within one epoch only, in the next batch, you push another 256 images till you finish uh, the whole thing, uh, whole 10,000 images. So if you see 235 out of 235, so that means you have pushed this batch size of 256 235 times in the single epoch. And then again in the next epoch, you push this 256 images with 235 times. So this will be different to 256 images till you complete your whole data set. Okay. So this data set value, the total number of images, total number of training examples that you have would be 256 times 235, right? So this is the total number of images that you have, right? Okay. Okay. So we saw autoencoders. So again, you have to experiment with this data set. Otherwise, you won't be able to grasp all the concepts, right? So now we would see. So we're doing convolutional neural networks. So here you start with first reading the data. So as I said, this is the MNIST data. So you have this, pixel values. So 784 pixels, right? And you have 42,000 images, right? So this is what you have, right? In your training data, in your testing data, you have 28,000 images of 784 pixels each, right? Okay. So these are some pre-processing steps. This is how an image looks like. This is an image of a one. Okay. So if you can see, this is a bit tilted, but your model should be robust enough to, you know, identify this identifies this number. Okay. Okay. Similarly, now what you do is that you pass your pixels of all these images that you have. So let's say these are the pixel values of the image that you have. So what you do, you convolve it with a filter. So this is what is called filter is a smaller uh, matrix. So in this case, you see the image is 7 cross 7 image, or and your filter is a 3 cross 3 uh, image. So you convert this by convolution. I mean you just multiply the filter with the source pixel, pixel by pixel, basically source image pixel by pixel. For example, you multiply 0 by 4, then again this 0 by 0, this 0 with 0, and again do the remaining things, add them all up. So this is what is taking place, and the addition adds up to -8, and value of -8 over here somewhere in the middle. Okay, and then you shift this filter one step at a time, and you calculate what is the convolution value, and you do you know make a new matrix, new uh, reduced dimension pixelated value. Okay, you obtain a new image with a reduced dimension. Okay, this is the new pixel value. Okay, so this is the first step that we saw in our slide. So if you see in this image, so this is the convolution. Okay, first convolution plus ReLU. So you just put this whatever value that you get. So this is, let's say, one of the convolved image. You pass these values, all these values, through this ReLU function. So what ReLU function does? is, as I said, if the value is greater than 0, it takes that value. So 15 greater than 0 is 15, whereas minus 110, it reduces it to 0, right? And that's the convolution plus ReLU. And this is the padding step. So I will not explain. You should look at what this step does. I will not explain it here. And this is one of your homeworks. So after padding, what you do is that you pool the features. So for example, pooling could be it could be max pooling, mean pooling. So in this case, we are doing max pooling. For example, you take the set of 4 pixels and check what is the maximum of these 4 pixels. So 2, 2, 3, and 1.5. So 3 is the maximum. You put the maximum value over here. Similarly, you do it for all the remaining. So 5 is the maximum. 5 you do. So that is the pooling. Okay. And then flattening. What you do is after you do the pooling, you flatten the data. So basically, if you have 1, 2, 3, 4, you flatten it as 1, 2, 3, 4. So just make it a column. And then you put this column in the input layer. And then you do the conventional neural networks that you have, right? And so on. So this is the flattening step. This is the uh, neural network dense layer steps. So these are called basically dense layers. Okay. So if you see, this is where we build the model, right? So for example, we start with the sequential model. We add the convolution filters with 8. Filter size is 8. Sorry, kernel size is 5.5. We need 8 filters. We use the activation ReLU function. Your input dimension shape is this. And after that, you add a pooling layer, pooling size of 2 cross 2. And then you add a dropout layer. So dropout is something which is also very important. So instead of keeping, so let's say so they did the dropout after max pooling. So what happens after max pooling? So if you have the pooled feature, so instead of using all the features, you can drop out some of the features. So let's say you drop out the second pixel and the third pixel, right? So in this way, you can drop out some of the pixels. So here 0.25, that means 25% of the pixels will be dropped out. So that is another dimensionality reduction step that's happening over here. And then again, you add another convolution, another pooling layer, another dropout, and finally you flatten the data, and then you add dense steps, and again dropout, and again another dense step. So by the dense step, I mean this hidden layers that you include. So in the first dense step, you use the activation function. Really, so this summarizes you of all the things that you have. For example, what is the input size of the first step, 28 cross 28 cross 8, and then what is the details of the max pooling dropout and so on. Okay, and finally, so see, so this is. Again, you use the optimizer. What is the optimizer that you are going to use? Atom optimizer. This is just for gradient descent. This is your learning rate. So beta 1 and beta 2 are some of the parameters that you need while using the atom optimizer. So what the atom optimizer does is it uses a weighted it uses the so for example, if let's say your learning rate is uh, in this iteration is something, and in the previous iteration it was something else. So it's a dynamic learning rate. Your learning rate is not always constant. Based on beta 1 and beta 2, your learning rate will get modified, right? And then you compile your model using this optimizer and using the loss function as category cross entropy, and you use the matrix accuracy, right? And this is the data augmentation step. So data augmentation, and what we do is that you basically take your original data and you transform your data. Maybe for example, let's say rotate it. So this 6 you see, you rotate this 6 so that your model can see all the variations of this number 6. So it can identify rotated 6 as well, not only when the 6 is written in the straight way. So this is an example of data augmentation. And then finally you fit the model in and you train it. So for example, here we have and epochs 10, and this is your validation data, and we finally you fit the model. So this is going to take a while uh, till you fit the model. Let me make the epoch size a little lower. Maybe then it will be faster. So let's take epochs equals to 1. Okay. Okay, so it will just do for one epoch. But you see, if you take more and more autoencoder example, right? For example, when you are going into the first epoch, your loss is 0.03, and then as you go into further and further epochs, your loss, basically your error decreases, right? That you see over here. So that's why we need to have more and more epochs, right? But you can try it out. I will have the notebook, and this is the you see this is the loss function. So you have 60% error, right? So your accuracy is 80%. To improve the accuracy, you have to you know uh, do more. Confusion matrix is explained in one. So I'll just quickly say that okay, this row means that this is actually 9 and also predicted as 9. So you have 386 samples which are actually 9. You have 8 samples which are actually 9 but are predicted as 7, right? Accuracy and so on by using more epochs and okay. Now coming to recurrent neural networks. Okay, so let's take the example of some stock data. Let's say IBM stock. So this is the IBM stock data that you have over time, right? So what you do is you just feed your uh, with the previous data, and you want to predict what will be the future stock price that's going to be, right? So for example, what we do is with this time series data, uh, so you take the first 60 days data, right? And using the first 60 day data, you want to predict the price of the 61st day, right? And then you take the next 60 days data and predict the price of the 61st day. And you do that so on. You train your model with inputs. So for example, your first input could be first 60 days data, and first output would be the 60 days data. And second input could be the second batch of 60 days and the 62nd days data and so on, right? So this way you train your model and again run it through multiple epochs. In this case I'm doing it for 10 epochs, right? And you run your model, and these are some of the details of the model that you use. So what are the layers? So all these LSTM layers you have to add. So again, this is a homework. So we look into this. What are the you know uh, units that you are adding? For example, 50 units, 20, and these are dense layers. And what are these? Dropout ratio is 0.2, right? So this is just a way to show that how powerful this. I think you should get a better idea if you use this notebook and do some hands-on with it. But to get the performance data, we just plot the real price with our predicted price. So if you see in red is the real stock price, whereas in blue we have plot uh, our prediction that is given by our RNN model, right? So yeah, so I guess this is it. And again, we calculate the root mean square error, which is error is 4%, right? And that's it. So I think we'll end here with RNN. Transfer learning is something which I'll not do over here, but I will keep it in the notebook. This is something for you to try out, right? And yeah, so this is something for yeah, so this is for something for you to try out, and you should. So I will just give you a brief idea about what transfer learning is while we look at the questions. We'll end with some questions uh, that we have over here. So yeah, so I was talking about transfer learning. Transfer learning is that these neural network model are very difficult to train. It takes a lot of time and a lot of data. So what happens is that has already trained somebody who has huge computational power and huge data. Big companies like Amazon and Facebook and all those people, they have trained their some model using their data with their computational performance. So they have built the network, they have trained the data, and they have got the weights of all these neurons, of all these neurons in the network. And what you do is you obtain their model and use those weights, use that model, and use your own data to predict your own data. So that is what transfer learning is all about, right? So, so you don't build your model from scratch. You take their model and you modify it according to your data, and you predict. Uh, you know, you make predictions using their model, their weights and biases, and so on. Okay, so these are some of the questions that you need to work on. Like I have shown how to construct AND gates, OR gates, and NOT gate. You need to construct NAND gate, NOR gate, XOR gate using neural networks, using the method that I described. Also, try all other activation functions in neural networks and implement them in Python. Not only activation function, you try to play with all the other parameters that I have used in the notebook that I have used while doing the CNN and the RNN and the activate and the autoencoder model. So what are the shortcomings of RNN? So there are some shortcomings. So look at vanishing end or exploding gradient problem, right? So there are some problems. So what happens is when you input feedback your model with the previous data, it can like blow up, right? If your weights are not optimized, it can blow up or it can vanish. So those are some of the shortcomings. How those shortcomings are overcome? So they are overcome using LSTMs and the decoder method. Okay. So these are some LSTMs stands for long and short-term memory models. So LSTMs form basic units of something called transformers. So there are more to it like word-to-vec encoding and so on, which are ultimately being used in models, large language models like ChatGPT and Copilot and so on, right? So this is a way to go into those. And finally, you try to implement, transfer learning algorithms to not only MNIST dataset, but also other datasets and, see which algorithm performs best. As I said that there are a lot of transfer learning algorithms that are available in the market, right? So try to use some of the algorithms on your own dataset and try to see how they perform, right? So yeah, I think it's a long video and long lecture, to be honest, and there are a lot uh, still to be covered actually in neural networks, which probably cannot be covered through this course alone. So I think you need to explore a lot of things on your own and try to see for this. But these are totally cutting edge, uh, topics that we see, and these are currently being used in all the industries, and there are a lot more to be done. So I think that's it. If you have any questions, please ask now.